So let us today do the analytic functions part of Unit 5. I'm Dr. Pankaj Agrawal from IMS Engineering College. Now, before we can learn about what exactly analytic functions are, so let us first recall what exactly the complex functions are. Now, we know that what exactly or how the complex variables are defined. Let us take an example of a simple complex variable defined as what z is equal to x plus of iy. So we know that x is your real part and y is your imaginary part. Now we can define this function fz as a complex variable function which has two basic parts. One is uxy. This is a function which has been defined out of these complex variables. And then we have another function vxy, which we would call as a imaginary function. So this would be your real function, and vxy would be your imaginary function. So now, rather than a simple variable which is real and imaginary, now we would start calling it as a real function, and we would start calling it as an imaginary function. The real function also would be defined in terms of x and y, and the imaginary function will also be defined in terms of x and y. So for example, let us suppose we have a function defined as suppose fz is equal to x square, right? So if we take the definition and expand the definition of z, which is x plus of iy, so we can write in this way, right? So after expanding it further, we get these terms, that is x square plus of iy whole square and plus of 2x dot iy, right? And since I square in complex numbers, you all know what is, it is negative. So we have x square minus of y square. So this term would be your real function part, right? Which is again defined in terms of both x and y. And rest of the term, which is 2x dot yi, would be now termed as what? Your imaginary part, which is again defined in terms of your x and y. So this is how we actually define a complex function. So now from this complex functions, let us define the definition of your analytic and non-analytic functions mathematically. So when a complex variable function has the following two properties, then we start calling it as what? Analytic functions. And what are these properties? So the first is that a complex variable function must be a single valued function, right? And then a complex variable function must be continuous and must have a unique derivative at each point in the domain it is been defined. So these are the two properties that any complex variable function, if follows, then we would start calling them as what? Analytic functions. And if any of these two properties are not being followed, then we would call that particular function to be a non-analytic function. Now, this analytic function actually satisfies a Cauchy-Riemann equation that we all know. We have studied that in basic mathematics. So let us first recall what this CR equation is and what are the conditions of or what are the requirements for CR equation. Now, the CR equation is defined over this complex valued function u plus of iv. So these are the two properties or the basic requirements for CR equation. First is the derivative of your u with respect to x must be equal to derivative of v with respect to your y. So this is the first requirement. And the second requirement is that the derivative of u with respect to y should be equal to the negative of derivative of v with respect to x. So if any given complex variable function follows these two properties, that is, if it follows or satisfies the CR equation, then we can talk about the analyticity of that particular function, right? Then we would start calling that function to be an analytic function. So let us take, so before taking few examples, let us also study the few important concepts. The first is singular point, or we call it a singularity concept. So if a function, say suppose fz, is not differentiable, say suppose at point z0, then that z0 we would call it as what? A singular point. So let us define an example. Suppose fz is given as suppose z minus of 6 divided by your z plus of 7. So what we need to do is we have to define a point z0 at which this function or we cannot differentiate this function. So very obviously, if we make this denominator part to be 0, then definitely we would not be able to differentiate this function. So what we need to look at is what if there is any point z0 at which this denominator can be equated to 0. So the simplest part of doing so is that just equate x z plus of 7 to 0, and we get the value of z is equal to minus of 7. So it means what? If we are going to put z is equal to minus 7 in the denominator part, so we know that this would become infinite, and we would not be able to find any derivative of your fz. And as per the definition, we know that this function fz, if it is not differentiable at z0, then it would be called as a singular point. So definitely this function for this function f0, it is not differentiable, and therefore this z0 is called a singular point. So the another important concept is of entire function. Now, function fz is differentiable everywhere in the complex domain wherever it has been defined. Then this function fz, we would start calling it to be a entire function, right? So let us take a few examples. Say, for example, ez or sin z, cos z, or cos x z. All these are examples of your entire function, because we would be able to differentiate these functions wherever defined in the complex domain. It would never reach to infinity. So therefore, we can consider them to be the entire functions. And definitely, the combinations of entire functions would also be what? Your entire functions, right? So, for example, if ez plus of sin z, this would be an entire function. So these entire functions, we would start calling them as what? Analytic functions also, right? So similarly, the sine of z square plus of e raised to the power of z, again, it is differentiable everywhere. So we can call them as what? The entire function, and thus they can be called as what? Your analytic functions. So let us take few important examples. Yes, in this case of tan z, which is defined as what? Sin z by cos z, this is not differentiable at every point, because we know that cos z can equal to 0, and therefore this would become what? Infinity, and therefore this tan z is not differentiable in that part. So therefore we can call that tan z is not an entire function, and therefore it is not an analytic function. So we'll take few examples. For example, I have been given, say, suppose fz is equal to z dash, which is nothing but it's a complex conjugate, right? So if you want to show that whether it is analytic or not, so we know that fz is defined as what? Since it is complex conjugate, this negative sign would get inserted. So x minus of iy is expanded in terms of fz, right? So if we what we need to show is the two properties that we have studied earlier. So here the u part is equal to x, and here the v part is suppose minus of y. So if I want to differentiate this u with respect to x, definitely it would give 1, and if you want to do it with respect to y, it would be 0. And similarly for this part, differentiating it with respect to x, 0, and differentiating with respect to y, it would give you minus 1. So over here, by looking at these conditions, so we can come to a conclusion that ux is over here is not equal to vy. And as per the requirement that we defined, the CR equation is not satisfied, and therefore this is not a analytic function, right? So this is how we can show that whether a given function is analytic or not. Let's take some few more examples. Suppose now we have been given fz is equal to z square, with where this is the absolute value of z. So by expanding it, since z can be written as x plus of iy, and since this absolute value of z can now be defined as what? Root of your x square plus of y square, and therefore z square would now become what? X square plus of y square. Now among this we have only what? Real part. So real part is defined over here as this, and since it does not have any imaginary part, so we can define it to be what? I dot product of 0. So this becomes the imaginary part, right? So again, doing the same thing, since u is this and v is 0. So after finding ux with respect to x, we get 2x, and with respect to y, we get 2y. and since this v is 0, so vx and vy would be 0. So again, the properties of CR would not be followed, satisfied, and therefore we can definitely call this to be a non-analytic function, right? Now let us take another example, which is fz is equal to 1 by z, and we need to show that this is a analytic function. So what we did is we expanded z in terms of your complex variable, that is x plus of iy, and then we have inserted specifically this term, that is your x minus of iy divided by x minus of iy, right? And then we can equate this. After solving this, we'll get this term, right? And then what we have done is, now what we need to do is we have to express it in terms of, suppose, u plus of iy, that is in a complex function form. So this part is your u, right? This is your imaginary part, and this part is your v, that is um, your sorry, this is your real part, and this becomes your imaginary part, right? So now what we need to do is, as per the definition and the two requirements for CR equation. So let us first calculate and equate del of u with respect to del of x, which comes out to be this function, this value. And I hope everyone knows how to differentiate your equations, right? So it's just a plain differentiation. And after doing that, what we get is this part. And similarly, we would find del of u with respect to del of y, which would give you this term. And in the similar manner, we would find del of v with respect to del of x, which gives you this term, right? And lastly, but del of v with respect to del of y, which gives you this particular term. So if you can see that what we get over here is, we find that del of u with respect to del of x is equal to same as del of v with respect to del of what? Y. And that is what we want. And similarly, the second part is also satisfying. That is del of u with respect to y is also equal to the negative of del of v with respect to del of x. So since both the parts of the CR equations are being satisfied, so we can call them analytic function. So this is an example of analytic function. Thank you for this lecture.